Hello and welcome to this video in this Pytorch tutorial series. This video marks the start of section 4, where we're looking at convolutions and convolutional neural networks. So in this video, we're just going to be looking at the basics of implementing convolutions, or 2D convolutions, in Pytorch. If you're unfamiliar with convolution operation, we'll talk a little bit about it here, but I recommend these two videos or video series to go over the concepts and the basics of convolutions and what they are and what they're for. So as I said, in this video, we're going to look at how we can implement convolutions in Pytorch and how we can implement a learnable convolutional layer. The first thing we're going to have a look at is just this convolution visualizer here. So this is just a simple interactive convolution plotter where we can kind of see the result of changing a whole bunch of different parameters of our convolution, and we're going to look at these parameters in some detail when we implement our layer. But for now, I just wanted to point it out because I'm going to go back to this, how we can see our convolution striding over our input, and we can see our output here. We can change the kernel size, the padding, the dilation, which we won't touch too much, and also the stride. Okay. First, before we get into CNNs and convolutional layers, what we're going to do is we're just going to manually implement a convolutional kernel, a convolutional feature extractor. So as you know, if you've gone through those videos or you already have some familiarity with the concept, our convolutions are some little kernel of features, some values that stride over our input, and at every point we multiply each value in our weights of our kernel by the corresponding values of the input, and then we sum them together and we get our one output. So this is for a single 2D feature input that gives us a single 2D feature map on our output. So again, some terminology. Our kernel of our weights is, in our 2D case, 2D, though if it has multiple channels, it'll be 3D, but we'll get to that in a moment. And our output we commonly call our feature map in our convolutional neural networks. But we'll get to more of that as well. So what we're going to do is we're going to take this input image here. So our image is of this puppy. And what we're going to do is we're going to construct a convolutional kernel, a well-known one called the Sobel edge detector. So I'm going to take this image quickly. We've opened it as a pill image with pill.image.open. And we're just going to convert that to a Pytorch tensor and resize it to be 512 on the shortest edge by just using some torch transforms. So my test image now is a 3 by 512 by 767. And we talked a bit about in the previous section when we looked at the MNIST data that Pytorch expects channels height width as our actual image size or image shape. So channels height width. Okay. So our Sobel edge detector, well, as the name suggests, it's an edge detector. I won't go into too much detail on how we derive this, but you can think of it as a derivative or a local derivative of our image. And it comes in, well, it has two components. It has the X and the Y component. So we have the derivative or the change in the X and the change in the Y direction. And we can combine those two together to actually get a gradient magnitude. And hopefully, as a result, we get all the edges. So here's an example image here where all the edges of the various objects in our image are highlighted. And this works because those edges are areas of high contrast. So we go from, a low or high intensity for white to black. So this edge here is marked by a large change in the actual values of our image. And our Sobel edge detector uses that conceptually to define an edge. So you can kind of look at the values of our kernel, and this is for an X direction kernel. We have -1, -2, 1, and then zeros, and then the positives 1, 2, 1. And you can imagine that when this is on an edge, say we have very large values on one side and very low values on the other, this will give us a high value. Maybe we'll have a look at what I mean there. So if we imagine we have some image patch where we're going from, say, white to black. This is going to be a 2 by 2 patch. And I'm just going to do a very basic version of this, -1, -1, 1, 1. Noting that for black values, they're very small values, so imagine that's 1. Imagine our white values, our 0 and our white values are high, so let's imagine they're 1. In the case where, let's ignore this for now. The case where, let's say, all our values are exactly the same, again, our kernel is going to multiply each value. Maybe I'll change the color. Multiply each value by the corresponding input. And then sum them up, and we'll get a single output value in this case. And you normally stride it along the image. So in the case where the input is all the same for that kernel patch, well, these are all zeros. Even if they were all ones, we have 1 times 1 or 0, right? If they were all the same, then the result from this will just give us 0. So if that's, obviously in this case, it's all zeros, so that's pretty easy, but maybe make it more interesting, where this is all now ones. So -1 times 1 plus 1 times 1 is 0. -1 times 1 plus 1 times 1 is also 0. So this is a 2D basic of our Sobel edge detector, but the same thing is true for our 3 by 3, right? This returns very low values when the image is constant or the values are constant, and only returns large values or returns larger values when the actual image has a lot of change. There's a high amount of difference in the image. So in the case where we could go from ones to maybe zeros, in this case we have -1 times 1, -1 times 1, and then 1 times 0, 1 times 0. That's going to give us -2 now. Or in the opposite case, where this is 0 and this is 1, so the opposite will be +2. So it gives us a large magnitude, not necessarily positive large, but a large magnitude when we hit an edge effectively. It's a very quick rundown of our Sobel edge detector. You can have a look at more detail if you're interested. And you can make them larger again, but again, kind of think of them as the derivative in a certain direction, the change, which gives us or defines our edge. So how do we do this in Pytorch with our Pytorch convolutions operations? So the first thing we need to do is to define our kernels. And in Pytorch, our kernel shape is output, which is usually 1, by input, by height, by width. So in our case here, we have a 3-channel, where is it? A 3-channel height by width, a 3-channel input. So our kernels are also going to be 3 channels. Now, one thing I want to just highlight is that our conv outputs, the outputs of our conv2D are always going to be a 2D output. So in our case here, we have not 1 channel on the input, but we have 3. So imagine it's not just 2 by 2, we have 2 extra channels on the input, like so. And our kernel will be also 3 channels. So again, this is at 2 by 2, but our kernel will also have those 3 channels. In either case, 1 channel or however many channels, the output was always going to be a single channel output. Okay, it's always going to return a single channel. Even if our input is multiple channels, that just means that our kernel is also going to be multiple channels. So let's assume that our kernel is 1 by 1. It'll also have 3 channels, and in this case it'll actually return, assuming stride of 1, a 2 by 2 output, but it'll only be a 1 by 2 by 2, even though this is a 3 by 2 by 2, and this is a 3 by 1 by 1. So this will stride across the input, right? But it will sum across the channels to give us our single value, right? And again, we'll see this in a bit more detail in a moment, but how we get more channels on our output is by having more kernels. Okay. So in our X direction, it's the same as the picture, right? And I've just repeated this along that channel direction, so it's the same kernel 3 times. We could just turn this into a grayscale image and just have a single channel, but I just wanted to show how our kernel can have 3 channels. Again, the first dimension is an output dimension, but don't worry about that too much now. And then we define the Y direction. So it's kind of going up and down, and that's kind of just the transpose of our, well, not quite the transpose, so it could be just the other way around. I've defined it a little bit differently, but effectively same thing in the Y direction now. So not going across, going down. And again, I've repeated that across the channel dimension. Okay. So this is the expectation. This is the kernel shape that Pytorch is expecting for its conv2d function. We have output or mini batch size by channel in by height by width. Okay. So our kernel can have multiple values in the output channels, but that's just the number of kernels. And we'll see that in a second. So first thing I'm going to do is I'm going to do each of the X and Y kernels on our input independently of each other. So here I've got my input. I have added the initial batch dimension, unsqueezed dimension 0, and I've defined my weights, which is gx. Bias is none, so your kernels can also have a bias with them. So that's just a single value per kernel, per whole kernel, a single value. And our stride, as hopefully you're familiar, our stride is just how far we're stepping over our input each time. You can make it larger, so you do 2 steps. And of course that will result in a smaller output size. So stride 1. And there we go. That's the result of our convolution. You can see what we've got here is effectively all the edges in the X direction. So not really any of the edges in the Y direction, like maybe this tail. It's a bit blurry, but the top of the head, don't have that too much, but you can see the hair standing up in that X direction is being picked up. We can do the same thing in the Y direction. You can see we now have more of the ridge of the top of the head and more of the actual tail, because that's kind of in the Y direction. Okay, so we can combine these 2 outputs together by just finding the magnitude of them both. So we just square both of them. Again, remember our output of our conv gives us a large magnitude value when there's a high activation, or when there's a edge, in our case with our Sobel edge detector. So if we square that, sum them together, get the square root, we'll get the combined magnitude. So we square them, we just get the magnitude, we add them together, take the square root, we get effectively the RMS magnitude of the gradient at any point, which hopefully will give us the edges of our image. So there we go. That is the Sobel edge detector, just a 3x3 Sobel edge detector that you may have seen before, and how we can implement that in Pytorch. This cell here, I'm just showing how we can actually combine the 2 kernels into one kernel by concatenating them on this output channel. So I'll just run this. We should get the exact same output. But if we look at gxy, the shape of this kernel now, you can see we've got 2x3x3x3. That first dimension, 2 here, is defining the number of output channels, or the number of kernels. So think of that first dimension as the number of kernels, the number of 2D outputs. Each of those outputs are created independently with 2 independent 3x3x3 kernels. Okay, I just wanted to make sure I've drilled that home. The output is not some combination of the kernels. Each of those kernels kind of scans over the image independently, and we get 2 separate output feature maps. And then I'm just take that output of our convolution, and then I could just do the power and then sum over that channel dimension and then take the square root, effectively doing the exact same operation as before. So that's how we can manually create or handcraft some features or feature extractor, which is what our Sobel edge detector is, to manually perform convolutions in Pytorch. So hopefully that was pretty straightforward. Just making sure that again, that our input is the correct size by unsqueezing, adding that batch dimension, and then our kernel is also the same, or the right size, output channels, input, height, width of our kernels. So our kernels don't necessarily need to be square, they don't need to have stride 1, they can have padding, and we can change a whole bunch of parameters, but we won't change too much now. But what we'll look at is how we can train or learn the parameters of a kernel or a convolutional kernel. So here we hand defined the actual values. Again, we've derived this kernel by looking at 2D derivatives. We've constructed this kernel and performed the convolution to get our edges, or the magnitude of the gradient that we're going to say are our edges. But the whole point of machine learning is that we want to get or have some algorithm that automatically learn to extract features, or automatically learn to extract some aspect of our data. Now, traditionally, you could just hand define a whole bunch of kernels, and this was done traditionally, or use some other method other than gradient descent to get a whole bunch of kernels. There's a huge number of sort of handcrafted features you can use, frequency detectors, blurring, and all sorts of things that you could hand create a whole bunch of kernels. And then one thing you could do is independently convolve your input image with all these different kernels, and then maybe sort of downsample your input image, and then use something like linear regression or even nonlinear regression with an MLP to actually then classify, predict, regress to something, right? But the idea behind our convolutional neural networks is that we don't want to just train linear layers. We want to learn the parameters of that kernel so that we can extract the relevant features that'll be useful for classification and regression. Maybe the edges are useful, maybe it's something else, maybe it's something more abstract that's harder to define, and that's effectively what we use machine learning for, right? What happens when you don't know what you're looking for, you don't know what features are going to be useful or relevant, and so we can use machine learning on our convolutional kernel in the same way. So why do we want to use convolutions instead of just linear layers? There's a number of different reasons. One being that for larger inputs, like this image, or even once we've downsampled, if you were to use a linear layer, the number of parameters that you need scale up dramatically, right? So the input layer for our MNIST MLP was 784 times the output of that layer size. We quickly scale into the millions of parameters per layer. And not only can that cause problems with overfitting, but as well, our linear operations have to sort of relearn the same features for different locations of our image. So if I just draw out an example of that, say we have our MNIST image, or something like that. And imagine we have, a 1 in the corner of our image here, and we have a different image where we have a 1 over here. If I was to break this image up into its individual pixels and, put that through our neural network with all the parameters and whatnot to everything, then every single one of these hidden layers will see every single pixel as the input, and there'll be one weight for every one of these hidden layer neurons, or whatever you want to call them. There'll be one parameter for every single input pixel. And so if our image is over here in the image, then all the weights and the parameters for each of these hidden layers, and then again, they're different parameters for every single pixel, for every single hidden layer, will need to learn how to recognize a 1. But if the 1 is over here, well, the parameters that have learnt how to detect the 1, well, they're looking over here, they're not looking over here. So that means that the parameters that are looking over here also need to learn what a 1 looks like, right? And the idea behind a convolution, or convolutional neural networks, and using convolutions and learning the parameters, is that if I learn a kernel, then that kernel will stride over my input. So my kernel will stride over the input. So if it learns to detect a 1 over here, well, it's also going to learn to detect the 1 over here, right? What we call this is translation invariant. Basically, because of the operation of our convolution, if it learns to extract features that help to detect a 1, it doesn't matter where they are in the image. translationally, because our kernel will translate or convolve over the input image and be able to detect the features of the image. It won't necessarily detect a one, but maybe it'll learn to detect the top of the one. We start with our low level features, the top of the one. It doesn't matter if the top of the one's over there or over here, it'll still be able to detect that. And then lower layers can combine different features, different aspects to build up this idea of a one. We'll go into more detail about this in the next video when we actually construct a convolutional neural network. Right. So yeah, that's one of the reasons why we use convolutions. We can effectively perform the same operation with far less parameters, right? And if we look back again at this, like I said, for our MNIST classifier, we had 784 input, and then let's say 256 outputs, and that's 784 times 256 for a single layer. But if I was to have, let's say, 16 convolutional kernels, and they were all sorry, it'd be one channel, MNIST is one channel by 3 by 3, right? Then the number of parameters in my first layer are 16 times 3 by 3, or 9 times 16. Do some quick maths. That's 144 parameters, whereas 784 times 256 is 200,000. Right, so we can have a lot more kernels, a lot more feature extractors that are basically reusing that feature extraction ability in more places over the image, and can hopefully circumvent potentially overfitting. So again, we're using convolutions because of some aspect of image data that we know. We know that a one in one part of the image is exactly the same as a one in a different part, right? If you're looking to classify, right? If you're looking to classify cats versus dogs, it doesn't matter if this dog is shifted or even rotated, then it's the same dog, right? And again, while a kernel or feature extractor can't handle rotations per se, because we're building up from low-level features to high-level features, a corner, an edge, a point is still the same if the image is rotated, and you can use that to build up this representation of what's actually in the image. But we'll go into more detail of that in the next video. Okay, so this little animation here kind of shows what I was talking about before, how if our input is, say, an image, a 3-channel RGB, the output is still a 2D output. A kernel is just going to be a 3-channel kernel, giving us a single 2D output. But like I said, once we move on to CNNs, we don't necessarily have a single kernel per layer. We can have multiple kernels. And what happens is each kernel, you can think of it as each kernel operating on an input independently, and then we're stacking that 2D feature maps, all those 2D feature maps together along the channel dimension, like I showed in here. Okay. One more thing I'm going to point out before we get onto constructing our convolutional layer is that the operation of a convolution, if you've ever tried to implement it yourself, can be actually quite time consuming. You have this little window, it needs to sort of stroll over your input, and a lot of people implement it with a nested for loop. However, that's very inefficient, and a lot of these accelerated frameworks and toolkits don't actually implement convolutions that way. They actually turn the convolution into a matrix multiplication, and because they're highly optimized, Pytorch is highly optimized for linear algebra, for matrix multiplication, and hardware GPUs are highly optimized for those matrix multiplications. By doing so, we can vastly speed up the performance of our convolution. Now, the actual way you convert your sliding window convolution into the block matrix, and you do the cyclic rotation of your kernel parameters and turn it into eventually your, your actual matrix for your input and your parameters is quite complicated. So I'm not going to go over it here. It's just something that I wanted to point out, that this is actually what's going on under the hood. We're not performing the sort of sliding window. Another thing I wanted to point out is that even though our sort of kernel might be small, the matrix, the resulting matrix can be quite a lot larger. And we often have to, or we have to pad it out with quite a lot of zeros. As a result of the operations we do to get it into this form, we are left with a whole lot of zeros. And if you know anything about multiplication, multiplying something by zeros or multiplying 0 by something is always going to result into 0. So you can kind of think of it, or it's sometimes referred to as a no-op. It's not really, but we're always going to get a 0. And so you can kind of think of it as a wasted operation. But because we've converted it into this form, we need to do this multiply by zeros. And as a result, you'll often see in some frameworks, but mostly in hardware and with our GPU, with our other accelerators, you'll see there's something like, optimized for no-ops, optimized for sparse matrices, which is what we call these with lots of zeros, or optimized for, or optimized zero multiplications, whatever the marketing term is. Basically, it's saying that there's some hardware or some specialty instruction in the hardware that handles a multiply by 0, because if you see that one of your operands, one of your inputs is 0, you don't need to perform the multiplication. You can just return a 0 straight away. With this small example here, there's a handful of zeros, but with larger inputs, larger kernels, that can quickly run into the thousands of 0 multiplied by zeros that we don't have to do anymore. And so you'll often see that in the marketing material somewhere. They've implemented this, and it's been, a lot of hardware these days has it, but it's just, again, you don't need to know, but it's something interesting to point out. So if you ever see that, that's what it is. That's what they're referring to. This is why it's so important, or one of the reasons why. There are other operations that have the same issue, but again, convolutions are a big one. Okay, so let's finally get on to actually implementing a learnable convolutional kernel. And it's quite simple to do. All we need to do, just like our linear layer in NN, in the neural networks module, we create a conv2D kernel, and we need to specify a few things. We need to specify the number of input channels. Again, that's the number of channels that our input has, either the input to the neural network or the input to this hidden layer, which was the output at the previous layer, or whatever. Output channels, like I said, you can think of this as the number of output 2D feature maps or the number of kernels. I like to think of it as the number of kernels this layer has, because each output, each kernel is going to produce one 2D output. So if you specify more channels, that's just more kernels performing independent operations. So kernel size, you can specify this as a tuple or tuple to get a non-square kernel. If I just specify it as an integer, that'll just be a square 3 by 3. Same with the stride. In the padding, you can specify a non-square stride. So you stride different amounts in different directions, X or Y. And then padding defines the zero padding, or there are other types of padding, reflection padding as well. Basically just defines how many, in our case 0, which is the default, you put on the input. Why might you want to do that? Well, it helps you not change the input size. This combination I've used here, 3, 1, 1, 3 by 3 kernel, stride 1 by 1, padding 1 by 1. If I go to my visualizer again, you'll note that, when I stride back to 1, the input size and output size are exactly the same. So 3, 1, 1 is very common. You see it a lot because it doesn't actually downsample the input size. The kernel's small and it won't downsample our image. You can also do a kernel 1, 1, 1. So that's a 1 by 1 kernel. Padding, I want that to be 0. I won't change it. There we go. 1, 1, 1. The issue with this is that it doesn't actually combine any spatial information. It's purely only channel-wise, which is another operation you'll see. If you just do a 1 by 1 by 1, again, any odd kernel size and padding of 2 divided by kernel size, floored operation, so 5 divided by 2 is 2.5, floor that 2 for your padding, will also give you the same input size. So you also see 7, 3, 1, but as you add more and more padding, right, we get into problems where most of your actual output is just padding. So that's why, a padding 1 kernel size 3 is often used. If you want really deep neural networks, right, and you have a small input, but you want to have lots of layers, if you don't have that padding, we've got 6 by 6 here, let's put that into our input, it's 4 by 4, eventually, right, your output's just going to shrink to something smaller than the kernel. And if that happens, Pytorch will give you a warning and say, hey, your input is smaller than the kernel size. I can't handle that. So if you want lots of layers stacked on top of each other, using something like this arrangement will mean you can keep keep adding layers, and your output won't change size. Okay, and so that's effectively what I've got here. I've got a kernel, one single kernel, 3 by 3 by 3. That won't change the size of the input. So that's the parameters of our kernel. You access that exactly the same as your linear layer. Again, I set bias to false, but if I didn't, you can see we've got one single bias per kernel. It's not per kernel, there's a bias or something like that. Spatially, maybe some people might think of that, but one bias per kernel, 3 kernels, 3 biases, etc., etc. But got one here. Okay. Good. So let's just pass our input through this randomly initialized convolutional kernel. So if you actually go into the documentation to talk about how they initialize the parameters of the conv, it's a bit different to how they initialize the linear layer. The linear layer, it's effectively initialized by a normal distribution, but the standard deviation of which changes with the output size. Again, this whole paper is talking about why you do that. Just the conv kernels are actually initialized in a different way. Again, this whole paper's describing how you would initialize this. Just again, pointing out that they are initialized differently. So simple forward pass, exactly the same as we would with a nn.module, any other nn.module. Conv is also an nn.module. Same with the linear layer, whatever. Again, just making sure the input of our conv layer is batch size by channels, by height, by width. Again, that's why I'm unsqueezing, adding that batch dimension. And then I'm taking my output and just plotting it in grayscale. So my output should be the exact same shape as the input. One single channel, 512, 767, same as my input. One channel on the output, even though there were 3 channels on the input. Okay. So what we're going to do now is we're going to train this convolutional kernel. So how are we going to do that? Well, we're going to create this target, this ground truth, and what this is going to be is just our original image, subtracted a very blurred version. So I'm used another Pytorch transform, a Gaussian blur with a 7 by 7 kernel and a sigma of 4. So it's going to blur our input image, wherever it is, a lot, and we're going to subtract that from our input. So the blurring is going to get rid of a lot of the high frequency components, and then by subtracting that from our original image, we're going to basically remove the high frequency components. And this is sort of another hacky way of getting the sort of edges of our image. The edges are the high frequency components. As you can see, it's not as good as our Sobel edge detector, but it is a way of quickly getting the high frequency components, which are kind of our edges of our input image. So I want to train a kernel that sort of returns this with a hope that as a result, because we're not subtracting from the input image, it's not just going to blur. We want to maybe get something like one of these 2 kernels. Okay, so how do we train it? Well, we train it exactly the same way as we would with a linear layer or even our MLP. We do our forward pass, our loss calculation, which I'm just going to do as an mean squared error. We zero the gradient, we backpropagate, and we take an optimization step. So I've also defined an SGD, stochastic gradient descent optimizer here with our kernel parameters. Okay, so this is going to take a little time. I found that to get a good convergence, it's easy to, or useful to go low and slow. So I'll get back once this is finished and we'll see what the output looks like. Okay, so it's finished training. You can see our loss has gone down. Don't be fooled by the very sharp fall at the start. If I sort of look near the end, you can see there's a big drop at the start. I think that's just because the output was very large in magnitude. Because we've done the subtract, our target is quite small in magnitude, the values. So big drop quickly, and then we converge to a relatively good output, much slower. So here's the original target, and here is the output of the kernel we trained. So you can see this output here is very similar to sort of combination-ish of our actual Sobol outputs. And it's a bit hard to interpret what exactly our kernel is. So this is one channel of our kernel. We actually look at the parameters. It's a bit hard to interpret, but maybe something similar to Sobol. So you can see we've got a lot of negative values here. We've got some positive values here. So maybe it's tried to combine the X and Y directions, but again, we know what it's trying to do. How it's doing it is a bit hard to interpret, but maybe if we take the average over this dimension instead, yeah, you can kind of see we've got high values or positive values on one side, negative values on the other. Let's just verify that. Yeah, you can see we've got negative values here and positive values on the other side. So maybe it's trying to do something like that, but you can see the result we get is very similar. In any case, that's how we train our convolutional kernel. Again, our convolutional kernel is only 3 by 3. It's only very small, and it's operated as this whole image, right? So there's not a parameter per input to output. It's just this little kernel moving over it, and we're optimizing that little 3 by 3 by 3 kernel so that we get something close to this output. Again, not like a fully connected layer. Fully connected layer, our linear layers, our perceptrons, all the same thing. Fully connected describes how every input is connected to every output of that layer. Our convolutions are no longer like that. You can imagine how many parameters we'd need if we were using a linear layer for this operation, but instead we've got 3 by 3 by 3, right? We've got, what, 27 parameters, far fewer than we would otherwise have to get this little edge. Okay, so we've just gone over some basics of Pytorch and convolutions in this video. If you like that, remember to like and subscribe. And in the next video, we'll be looking at how we can actually implement or use these convolutions in a multi-layer neural network to get our deep convolutional neural networks. So I'll see you in the next one.